Hi everyone, welcome to this lecture on a simple energy balance model for the planet Earth. Now what we're going to do in this lesson is write down a basic differential equation, just a first order differential equation for the temperature of the Earth over time. Now the temperature of the Earth over time is a huge question as we grapple with climate change and try to figure out what's going to happen in 10 years, 50 years, 100 years, etc. If you want to make a prediction over a short term, then I think you would need a lot of parameters. If you think about all of the different factors that go into the temperature of the Earth, they range from things very far away, like solar flares, to what we humans do. So I put on this slide a graphic from Introduction to Climate Modeling by Thomas Stalker that shows you the levels of complexity that you can create. Now, if you wanted to model climate on Earth, your two biggest components would be the ocean and the atmosphere. Each of these bodies could be modeled using 0, 1, 2, or 3 dimensions. So if you wanted to create an incredibly complex model that captured as much of the parameters as you wanted to deal with the ocean and the atmosphere, you might want to have latitude, longitude, then also depth. So you'd have 3 dimensions going into each component, and then you have all of your other considerations on top of that. That is not what we are going to do today. What we are going to do today is an EBM point model. So we are not going to distinguish any dimensions of the ocean or the atmosphere. We're just going to treat the Earth as one object. So considering how incredibly complex the environment is, our model will be about as simple as it can be. However, what we'll see is that our model, even though it feels just like an overly simple toy model for the Earth, does capture some really interesting aspects of how the temperature on Earth has evolved over time. Our energy balance model is going to model how the average surface temperature of the entire Earth, treated as one object, behaves based on only a few parameters. These are like your biggest parameters when you're trying to model the Earth. The first parameter is one that we will just treat as a constant. So this parameter we're not really going to play around with too much, but this is solar radiation. That's just a measure of energy coming in from the sun, and we're going to model that with a single constant. Then emissivity, which we'll call epsilon, is the one that we're most interested in if we're thinking about, say, human actions on Earth. And this is the thickness of the atmosphere. And then lastly, albedo, which is also affected by human actions. This is the reflectiveness of the Earth. So is the Earth mostly reflective? Like if it were covered in ice, light hitting Earth would essentially just bounce off of it? Or is it dark so that it absorbs most energy and it doesn't reflect it back into space? The principle of our model is going to be to treat the temperature on Earth kind of like we treated closed populations. We will model how temperature changes on Earth as a balancing act between the energy coming in from the sun and the energy going out. So the principle behind that is like births and deaths for a closed population. So what we're going to do is piece together how much energy is going to come in, how much energy is going to go out, and then we'll do a balancing act between those two. Let's take a look at the energy that comes into the Earth. This is actually a multiple of the surface area of a disk whose radius is the same as the Earth. Now that's a funny statement because you think of the Earth as a sphere, not a disk. But imagine you're the sun looking at the Earth. From your perspective, the Earth looks like a disk. So the light coming in from the sun, here not drawn to scale, is going to treat the Earth like a 2-dimensional object, not a 3-dimensional object. So we see this pi re squared, that would be the area of a disk whose radius is the same as the radius of the Earth. Okay, so this is going to be our energy coming in. Pi times the radius of the Earth squared times 1 minus the albedo measurement times the solar radiation constant. The solar radiation is just a constant. We're not going to worry about that. 1 minus the albedo is measuring how much light is going to get bounced off. If the Earth were ice covered, the albedo would be approximately 1, which means that 1 minus alpha, 1 minus the albedo, would be almost 0. That would result in very little energy coming in because most of it would be reflected back into space. If there were no ice and the Earth was very dark, say it was ocean and forest, it would have a low albedo closer to 0. That means 1 minus alpha, 1 minus this albedo, would be larger. So you would be getting more energy coming in. The Earth would be darker, it would be absorbing more light. So this albedo term is between 0 and 1, and if you're wondering what the actual albedo of the Earth is, it would be about 0.3. That's the average albedo around the Earth. So the Earth is overall a fairly dark planet. Now what we want to do is judge, based on the temperature of the Earth, how much we would expect that energy coming in to be. It's a bit strange here because we want to plot energy with respect to temperature, but there is no temperature explicit in the right-hand side of our energy equation. However, the solar radiation constant is a constant, the radius of the Earth is a constant. The only thing here that's not a constant is the albedo. And it turns out the albedo depends on the temperature. So implicitly, this energy function is a function of temperature. That information is being passed from the temperature to the energy through the albedo. So what does that relationship look like? Well, it's a curve that takes this shape, but the idea with this shape is that if the Earth is very cold, so we have a low temperature, then it has a larger quantity of ice. In fact, it could even be ice covered. That would result in a high albedo and therefore low energy in. On the other hand, if the temperature were high, you would have very little ice and perhaps more forest or something like that, and your albedo would be lower. That means your energy coming in would be high. So we have these two extremes here. You can imagine an ice-covered planet and an ice-free planet. We're somewhere between the two. And what happens is that as you pass from a low temperature to a high temperature, the effect on the albedo and ultimately the energy is a fairly fast transition like we're looking at here. So it's not a linear rate or anything like that. You basically get rapid melting from an ice-covered state to an ice-free state. So this is how we'll model the energy coming in as a function of temperature, where we've created this shape based on our understanding of how we could pass from ice, perhaps all the way down to the equator, to an ice-free planet. Now let's talk about the energy going out. While the energy coming in is coming in from the sun, so it's not hitting the entire Earth as we saw, the energy emitted we want to picture is kind of radiating outward from the entire planet. So this is going to be directly proportional to the surface area of the entire planet, which is 4 pi, the radius of the Earth squared. Well, we multiply that by the emissivity, multiplied by something called the Stefan-Boltzmann constant, and then times the temperature raised to the 4th power. So let's talk through each of these. 4 pi, the radius of the Earth squared, that's a constant. The Stefan-Boltzmann is a constant. Now how the emissivity works is that was kind of like our thickness of the atmosphere calculation. So how we translate from emissivity to thickness of the atmosphere to the effect on energy out is a very low emissivity means a very thick atmosphere. So if we had a lot of greenhouse gases, we wouldn't emit a lot of energy back into space because it gets trapped inside close to the Earth by the atmosphere. On the other hand, if we had a very thin atmosphere and a high emissivity, then energy does get emitted back out into space, passing through the thinner atmosphere, and we'd have a larger energy out measurement. What we also see from this relationship is the hotter the planet, the more energy you emit. That's seen in that t to the 4th term. A colder body does not emit as much energy. So the warmer the planet, the more energy you emit. Unlike our equation for the energy coming in, here we do actually have temperature present in the right-hand side. So for any choice of the parameter emissivity, this is just a quartic polynomial in T. So there's no guesswork here about the shape of it. It's literally a quartic. So that's the picture that we have here. As temperature increases, the energy radiated out increases following the shape of something times T to the fourth. Okay, let's put them together. To figure out how the temperature on Earth changes, we want to compare how much energy is coming in versus how much energy is going out. If there's more energy coming in than out, then we would say the temperature would increase over time. On the other hand, if more energy is going out than coming in, then the temperature will decrease over time. So the way the temperature changes over time is going to be a balancing act between the energy in and the energy out. So we set up this equation where we're essentially saying the way the temperature changes is proportional to the difference between the energy in and the energy out. So we have a constant multiple times the rate of change of temperature with respect to time equals the energy in minus the energy out. So if we put in the equations for energy in and energy out that we've already seen, that's what we'll have on the right-hand side. The overall unit there is joules per second. Since the rate of change of temperature with respect to time is going to have a unit of kelvins per second, note that the unit on that constant multiple on the left-hand side should be joules per Kelvin. And then to simplify the terms a bit, what I'm going to do is go through and divide everything by 4 pi times the radius of the Earth squared. That cancels out nicely on the right-hand side, and then on the left-hand side, we'll just say that's the constant multiple divided by that, and we'll call that C. By taking, say, the energy in quantity and dividing it by 4 pi r squared, what we're essentially doing is looking at how much energy is coming in per square unit of the Earth, because we're dividing out by the total surface area of the entire Earth. So while we've canceled out some terms from our energy in and energy out equations, we won't change the shapes of the graphs that we've already seen, qualitatively speaking, because each one would be reduced by the same constant multiple. So in the next few slides, what we're going to do is look at the shape of the energy in and the energy out curve. It's going to be the same pictures that we've already seen, because again, all we've done is divide both the energy in and the energy out functions by the same constant multiple. The big question we want to answer is, how is the temperature going to change over time? And we're just trying to give a good picture of whether or not it's going to go up or down. The constant on the left-hand side is a positive constant, so we won't worry about that, which means the right-hand side determines the sign of dt dt. Unfortunate names, but that's d temperature, d time. Rate of change of temperature with respect to time. Whenever that right-hand side is positive, that means that the temperature will increase over time. Whenever it's negative, it means the temperature will decrease over time. So how do we determine the sign? Well, we're going to look at those two graphs that we put together for the energy coming in and the energy going out. Let's define different regions on this graph and then analyze how the temperature would change in those different regions. So what happens if we are in perhaps an ice-covered state? Suppose the temperature on the Earth is really, really cold. Well, as the temperature decreases, that quartic shrinks to 0. So we get a little bit more energy in than we have energy going out. That means in the balancing act between energy in and energy out, the right-hand side of our differential equation would be positive. So if we're in that region all the way on the left, the rate of temperature with respect to time would be positive, which means we would expect the temperature to rise. So if we put together now a phase line, I haven't identified them yet, but we have 3 fixed points, 3 equilibrium solutions where the rate of change of temperature with respect to time would be 0. So if we're in this zone to the left of the equilibrium solution A, then the rate of change of temperature is positive and we would increase towards A. What happens if we're right at A? Well, that would be an equilibrium solution, so the rate of change of temperature over time would be 0. Now what happens if we have a mid-low temperature, maybe not totally ice-covered, but still a very cold planet, putting us between the equilibrium solutions A and B? Well, based on the shape of our quartic, compared to our energy N curve, the quartic is higher. That means more energy is going out than coming in. So the right-hand side of our differential equation is negative, which means the rate of temperature over time is negative. So if we add that information to our phase line, if we are between the equilibrium solutions A and B, we would expect to decrease towards A. If we're right at B, however, that would be an equilibrium solution, so the rate of change of temperature with respect to time would be 0. Now what happens if we're between B and C, kind of like a mid-high planet? Perhaps there's still some ice, but it's a hotter planet than we've seen so far in this analysis. In this case, we have more energy coming in than going out because our energy in curve is higher than our energy out quartic polynomial. So with more energy coming in than going out, the rate of change of temperature over time would be positive. So when we add that to the phase line, we would go to the right, which means if the temperature is in here, we would expect the temperature to rise towards the equilibrium solution at C. Right at C, of course, we're at another equilibrium solution where the derivative of the temperature function would be 0. And then for the last zone, if we are higher than C, perhaps we're at a very hot, ice-free planet. Sometimes this is called hothouse Earth. Then we're actually emitting more energy out than having energy come in. And that's because that quartic polynomial is going to grow to infinity fairly fast as we travel to the right. So it's going to be taller, it's going to be higher than the energy in curve. So overall, the derivative of the temperature function would be negative. So our cold equilibrium and our hot equilibrium are both stable. And then our mid-range temperature equilibrium is unstable. So we have two stable states here. Now this whole analysis was based on the shape of these curves. Let's see how changing the emissivity will affect our analysis. Now in our modeling, the emissivity appeared as part of the coefficient of this quartic polynomial. So if we keep everything else the same and adjust just the emissivity, in other words, we're just going to adjust the amount of greenhouse gases in the atmosphere to change the thickness of the atmosphere. So that's going to have an effect on the shape of this quartic polynomial because it's part of the coefficient of that t to the fourth term. So when I put these two models together, I set the emissivity to be 0.6. That's what gave us these three intersections leading to three equilibrium solutions for this differential equation. Now, if I lower the amount of greenhouse gases in the atmosphere, that's going to increase the emissivity of the planet. So let's see what happens if we increase from 0.6 to 0.65. When we do that, our quartic gets a little bit steeper because we're increasing the coefficient of the t to the fourth term. We still have three equilibrium solutions. They still behave the same way. But if I increase a little bit more, say I go up to about 0.7176, the equilibrium solutions B and C have collided. I'm just calling it C here, but those two equilibrium solutions were pushed together. And then if I increase it a little bit more, so I reduce the greenhouse gases, making the atmosphere thinner, making the planet emit more energy back out into space, we're left with only one equilibrium solution in that cold state down to the left at A. What this phase line tells us is that if we are anywhere on this temperature range, either to the left of A, right at A, or to the right of A, it doesn't matter. Anywhere we are, long term, we would expect to arrive at A. A is the unique equilibrium solution, and it's a sink for the entire phase line. That means the only stable state for the planet in this scenario is an extremely cold temperature. I was really shocked when I learned this information. Whenever I thought of early Earth, like hundreds of millions to billions of years ago, I always pictured volcanoes and lava and explosions and really hot activity. But actually, the geological record indicates that there were probably several times that the Earth was ice covered or close to ice covered. Ice from the poles extended nearly down to the equator or all the way there. Anytime the Earth is essentially ice covered, they call it Snowball Earth, and they think it may have happened about 3 different times. And each of these times spanned millions of years in its own right, but I've just given you ballpark measurements here. So approximately 2.2 billion years ago, when the Earth was a fairly young planet. Again, you think of the young Earth 2.2 billion years ago, at least I think of it as really hot, but actually at some point it was mostly cold. And then there was another period of extreme glaciation about 700 million years ago. And then the Marinoan glaciation period was about 640 million years ago. Again, each of those periods would have spanned millions of years in its own right. It wasn't like an instant 640 million years ago. That final glaciation period would have overlapped with early life, of course. And one thing that's interesting, if you like biology, is the Cambrian period was just after that final glaciation event, at least just after in the grand scheme of the entire planet. Now, what's significant about the Cambrian period, that's when you had kind of the first complex multicellular life forms appear. So no longer unicellular life forms, but life forms which had greater levels of complexity. Most of these life forms would have been in the ocean. And in fact, you have sponges and jellyfish, and just a little after Cambrian period, horseshoe crabs all date from that period. So you can see actually kind of complicated creatures. If you like horseshoe crabs, be sure to go to the aquarium on the coast of North Carolina at Pine Knoll Shores. You can hold them. And when you look at these amazing creatures, they have such a prehistoric look to them. And that's because they're about as old as the Cambrian period. They haven't changed much since then. Now, what kind of creatures were around 2.2 billion years ago? Bacteria, cyanobacteria, that's still around today. But you had these simple unicellular organisms, not very complicated, but if you were going to survive these periods of glaciation, and as we'll talk about later, hot periods too, you had to be pretty hardy. So interestingly, these extreme Earth events may have led to the development of complicated, resilient creatures. Then we get our oldest known mammal fossils dating about 200 million years ago, just for a little perspective. So here's a question. If you're looking at this phase line here and you see that you have one sink and the entire phase line is being drawn towards A, why would the Earth ever be anything but a snowball? So how did the Earth escape this period? And the answer is that the Earth is more complicated than our models have captured. For example, you still have volcanoes. Volcanoes are releasing greenhouse gases into the air, and essentially you can keep changing that parameter so that your phase line doesn't always have to look like this. So let's now take it the other direction. What happens now if we increase the greenhouse gases in the atmosphere, lowering the emissivity? That way, less energy gets transmitted out into space. So ultimately, our quartic polynomial is going to go down. Okay, well, starting where we were with an emissivity parameter set to 0.6, if we lower it to 0.5, then the coefficient of our quartic has gone down. So we've lowered that quartic. You can see what's happening here. C is fine off to the right, but A and B have moved closer together. Now, at some point as we lower the emissivity, the equilibrium points at A and B collide. So now we just have a node on the left and then our stable equilibrium at C. If we lower the emissivity beyond that, we only have one remaining equilibrium solution up at C. So once again, we have one sink. This time it's in a very hot regime. If the temperature is anywhere on this phase line over time, you would trend towards that hot temperature up at C. Similar to how there are periods in the Earth's history when we think the Earth was mostly ice-covered, there were also periods when the Earth was extremely hot and would have had no ice, including at the poles. One of them was about 4.5 billion years ago. That's the period that I like to picture when I picture really hot explosions on Earth. I think that's what I'm imagining. Then if you look over on the right, I've included a graphic here that comes from the Smithsonian Institution's National Museum of Natural History, and it begins in this record about 500 million years ago. You can see about 500 million years ago it was extremely hot on Earth. The average global temperature was over 90 degrees Fahrenheit. That's the average temperature on the entire Earth. That's really hot. Then closer to the modern era, there was the Cretaceous hot greenhouse period about 92 million years ago, as well as the thermal maximum, I won't try to pronounce that, about 55 million years ago. So in this graph, you can see they've charted the data for hot periods on Earth and cold periods on Earth. You can observe extreme instances of both hot Earth and cold Earth, and what's really interesting is the rapid transitions between the two. So relative to the timescale here, I would say that this is a pretty rapid transition, as is this one and this one. So it looks like Earth went fairly rapidly from hot to cold, back to hot, and then back to mostly icy. Here's where we are today. So you hear sometimes that Earth is colder today than it has been in the past, and that's true. For all of human history, we've been on the colder side of things, but of course, it's trending up. So just like before, you can wonder why this scenario where we only have one sink for the entire phase line could lead to oscillations. And this time you get ways that the Earth can sequester greenhouse gases. For example, through weathering of the rocks and things like that. I mean, that happens over millions of years, and you can end up changing the emissivity of the atmosphere. So what we're going to do now is collect some of the information that we've gotten from our simple energy balance model, construct a bifurcation diagram, and then what I hope to illustrate with our bifurcation diagram is, in particular, these rapid transitions from hot to cold, and from cold back to hot. Okay, so as we ran through various emissivity values, we created phase lines, and now what we're going to do is take all these horizontally drawn phase lines and flip them vertically. That way, we'll treat the parameter, the emissivity, as an independent quantity, and we'll be able to see how adjusting the emissivity can lead to these multiple stable states or just one stable state, and altogether we'll create the bifurcation diagram. So here's what it looks like. Our starting default phase line was here with an emissivity of 0.6. And then we started removing greenhouse gases from the atmosphere until we had a single sink down at A. That's that point down here. That single point at A we thought of as corresponding to Snowball Earth events. On the other hand, if we increased to the right until we got hothouse Earth up at C, flipping those phase lines vertically looks like this, and then I've thrown in a few other dots as well. We piece all that information together and we get this S-shaped curve where we see the existence of two fold bifurcations. So let me highlight here that this top branch corresponded to the equilibrium solution we called C. That was one of our stable states. The middle branch corresponded to the equilibrium solution B. That was an unstable equilibrium, so in reality, you would never expect to see the Earth there because a slight perturbation would cause it to leave B and go to either A or C. And then the bottom branch was our cold equilibrium A. So both A and C were stable sinks on our phase line. Let's see if this bifurcation diagram now can illustrate how we could ever transition from something like a snowball Earth scenario to a hothouse Earth scenario and back again in a fairly short amount of time. Relatively speaking, of course, we're talking about millions of years. Okay, so suppose that we have a snowball Earth scenario. We're about 2.2 billion years ago, and the Earth is ice covered all the way down to the equator. Now, over time, volcanoes are going to release greenhouse gases into the atmosphere, decreasing the emissivity of the atmosphere. And so we expect to slide a little bit to the right on this bifurcation diagram. The temperature is going to increase. As the greenhouse gases and consequently the temperature increase more, we keep going to the right. It's a stable sink, so there's no reason why we would jump up to that unstable source or anything like that. We stay at our stable state, but our stable state is getting warmer and warmer. If the greenhouse gases increase enough, then our stable state transitions into a node. A little push off of that node and the Earth is going to jump all the way up to the stable state at C, corresponding to a hothouse Earth. So you can see that was a rapid transition from a cold planet to a hot planet. Now we have an ice-free Earth, but other processes on Earth are going to sequester greenhouse gases out of the atmosphere, increasing the emissivity of our planet and lowering the temperature. As the greenhouse gases go down, that would cause us to slide to the left. Again, we would stay at that stable equilibrium at C, but C's value itself is going to slide to the left. Now, eventually, we find ourselves at the node. If the greenhouse gases decrease a little bit more at that point, we're going to rapidly transition back down to a snowball Earth state. So these fold bifurcations we see allow us to jump from snowball Earth states to hothouse Earth states and back again as the emissivity of the planet changes. Now you might be wondering where on this diagram we are currently, and we're roughly here. So we are at the equilibrium value at C. Being down at A is really like a snowball Earth state. It's not the hottest it's ever been, right? We're on the cooler side of things. The way the Earth is going, there is no chance that we're going this way. Don't worry about that. The big concern is that we, humans, are putting enough greenhouse gases in the atmosphere that we're raising the overall temperature. The nuances involved in those questions, what human activity is doing, how it would affect the next 10 years, 20 years, that's not the kind of information that you're going to get out of this model. Really detailed climate models looking at all of those factors and making predictions over the next century are incredibly complex. They can take many, many, many years to develop. So our toy model that we've been looking at today is really just designed to describe the major properties of energy coming in versus energy going out over a time scale of millions of years. Thank you for your attention.